Hi Science 10, welcome to part 2 of 4.2, how to determine work when looking at a graph. So recall that our work formula was force times distance, and on a graph, force would be on this y-axis, force in newtons, and our distance would be here on the x-axis at the bottom. And to determine the work done, we just have to go back to how the formula is force times distance. Now, if you have a constant force, so every position that your item is, you continually have a force of 10 newtons, that's a pretty easy calculation because your work is actually everything under the line. So in order to do this question, you're simply going to say for work, you're going to do force times distance. So that'll be 10 newtons times 5 meters. So the 10 newtons times 5 meters will mean that there was 50 joules of work done in this example. Sometimes, however, the force can change. So in this case, the force started off as 0, but as they moved this object 5 meters, the force continually got stronger to the point that it was 8 newtons by the time the object was 5 meters moved. So in this case, you still have the same rule that the work done is everything under the line. So in this case, the only way to figure that out is, say, if I do calculate this entire rectangle of area, all I have to do is take half of it, and that will be this answer. So that's why when we do have this type of graph, we do work being half of the force times the distance. So in this case, the force was 8 newtons, and we multiply by the distance of 5 meters, but we must take only half of that. So 5 times 8 is 40, and half of 40 is 20. So 20 joules would be your answer for this particular graph. If you have something where the force changes, simply we would multiply, because we need to have this distance entirely. We would do force times distance of, over here, 100 times a distance of 20 for this section, and we could add it to this section where you can see you'd have to go half times the force times distance, and this one you could still say 100, because we're here, times a distance of 30 minus 20 is a total of 10, and you're going to get your 1,000, but it would have to be half of that, and your answer for this section would be 500 joules, and you could add it over here to the other 20 times 100 of 2,000 joules. So you could add the two portions of the graph together, and that way determine the entire work for this whole example. This kind of a graph would be a lot more tricky to do because it doesn't have straight lines. So what we can do if the shape is not uniform is we can actually count how much one little spot is on the graph. So we see that this one is 2 newtons going up and 1 meter going across. So we can see that for every little box, that will equal 1 times 2, which is 2 joules for every box. Then we count how many boxes are under the line, because remember, under the line is the amount of work that was done. So every box that's completely a square, that's very obvious. But when the ones that are not completely covered, what the rule is that you count the ones who have more than half the square under the graph. So you can see that that one was counted. You can see that this one was not. And so you would just count up all of, and you can put dots like they did here, count up how many boxes are under the graph, knowing that there's 2 joules per box. We count 46 boxes or squares on the graph that are significant, and they have more than half or all of it in under the line. And in this case, you would multiply the 2 joules, 46 boxes in total, and we're estimating around 92 joules of work was done. And of course, these are irregular, and so it's more or less realized and accepted that this is kind of an approximation. You're doing your best to figure out the total of area underneath a curved line. So in a case like this, you just have more work to do, because you would have to determine how many boxes and count them all up again, figure out how much a box has for its newtons. In this case, it was talking about 1 square being a kilonewton, as you notice over here. So we'd want to change that to 1,000 newtons so we can multiply it by the 2 meters. So we figure out 1 box worth is exactly 2,000 joules then, if you use newtons instead of kilonewtons. 1,000 newtons times 2 meters would be 2,000 joules. If you check them all out, it should add up to 46 squares. So 2,000 times 46 is an approximate 92,000 joules of work done underneath the line. Okay, so that's what you would have to do in that case. And this one has no grid, so we'll just skip that one. That was kind of a joke. Okay, you will see your assignment on Google Classroom. Thanks for listening on this talk on how to determine a work.